Okay, so today we're gonna continue and we'll see, maybe wrap up simple harmonic motion. Right, so this is just another application of trigonometry that we can use, that we find in everyday life. Yesterday I talked about springs and them bouncing back and forth. Okay, but obviously, that's not the only object that experiences simple harmonic motion. Um, Another example is your normal waves. Okay, waves in a pool or in a pond or something like that. Right. So if you drop a pebble and you see all the ripples that go out, well, if you kind of took a cross section and you were able to just look at, the waves from a side view, right? Those waves would be a sine or a cosine graph, right? They would show exactly how they are. Now, if you're in physics, you might have talked about particles in a wave, but it's actually, let's see if I can find. No, that's not what I'm looking for. So if we're talking about something like a wave in water, all right, if you think of it as water as a bunch of H2O molecules all packed together, when a wave happens, as the wave moves, the particle doesn't move along with the wave, right? So as like the crest of the wave is moving along, it's not carrying along the same particle the whole time. What happens is that particle kind of bobs up and down next to all the other particles. Uh, and I'm looking for, I thought I had, here we go. So it doesn't exactly bob up and down. It actually bobs in a more, am I sharing my screen? Yeah. Okay. It moves in kind of an elliptical motion. So this is when if you start getting into sound waves and stuff like that. But the water waves are what's called transverse waves. So here, right, as the wave it's called propagates as it moves, as the wave propagates from left to right or right to left, right, these particles kind of just are shifting up and down, right? So here you have all these dots that are water particles, or something that's in the water. So at the top of the wave, they're just kind of sitting there getting pushed back, but then they get pulled back, right? So they get pushed by the wave, but then as the wave recedes, it gets pulled back. If you move lower, okay, where the wave isn't as strong, as the wave's not as, it doesn't have such a big amplitude, then that motion gets tighter, right? But I don't know if you can see it. They have the same period, okay? It reaches the top at the same point, it reaches the bottom at the same time, okay? So they're all related that way. And all of this is simple harmonic motion, okay? It's periodic motion. Right, this is a more accurate example here. Okay, I guess this was updated in 2016. Oh, they both were. Oh, this is for an elastic solid, which is a little different than water. This is more like it's called a Newtonian fluid, which means it acts like a liquid in most parts, but if you apply a force, it becomes a little solid. All right, so all of this is simple harmonic motion. So a more physical example here, right? Here we have the actual spring. You can see it here. We're starting at an amplitude of 2. So I took this spring and I pushed it up until it was 2 whatever inches higher than its resting position, right? If I had it down here at 0, that would be the resting position. Here, we'll learn this either at the end of this year or you'll see it next year in AP Calc, is what's called the derivative. This is the speed. So this is saying the speed is 0. So I'm not pushing it down. I'm not moving it. I push it up. And then what happens is I just let it go and I let it do its thing. Right? So as it does its thing, right, if there's no friction, there's no air resistance, it's just going to keep bouncing up from that 2 to -2 forever. Okay, and here we can see as the time goes on, we can see why that graph gets made, right? So here, our x-axis is actually time. Okay, it's not a position, it's not x or y, right? So this is time going to the right. And here they actually, these two parts are actually a little more physics related. This is the mass of the weight, and the K is what's known as the spring constant, which tells us how elastic is the spring. A higher constant means it's tighter, it's harder to pull and push. A low K means that it's pretty flexible. Okay, and then with it, here they gave us our W, which tells us, or I'm sorry, our omega, which tells us, we saw that yesterday, and that helps us find our period and our frequency. All right, so those are directly related. So here, though, let's think about this. The period, the time it takes to get from this peak to this peak, maybe looks like 15 seconds. All right, so if I go to, yeah, just before 15, yeah, almost about 15 seconds would be a period here. Right, so it takes 15 seconds for the spring to return back to this position where I pushed it up. So from that, right? Okay, thank you for letting me know. So my period would be 15. So to find W, or omega, right, I would have 15 equals 2 pi over omega, and then I would solve for omega. So I would have 2 pi divided by 15 equals omega, and let's see, let's make sure that matches up. 2 pi divided by 15, divided by 15, and we see that 0.418, which I think 0.426. I guess it's not exactly 15, but it's close enough. Right, so that, I just wanted to show you a little actual physical example of what was happening with harmonic motion before we get back into the math part. Okay, any questions so far? All right.
I'm still kind of like.
Example that we did. What's up?
I'm still a bit confused on like W. Do you put like the period
Okay, yeah.
underneath?
So I'm going to talk about that when we start looking at examples in a second. So yeah, I'll talk about that more. One other thing I wanted to point out. Can't do that. All right. So remember, we have two different options for our harmonic motion. We can do sine or we can do cosine, right? Everything else is the same. You still have the amplitude, you still have the omega, which tells us our period or our frequency, and then you have time, which is, our independent variable. For this example, because I start up here, okay, because I'm not starting at the origin, for this particular example, I would be using my cosine function. All right. If I started at 0, and I did something like this, where I pushed it up with a velocity of 0.5, right, this would be the sine function because it starts at the origin. It has a neutral start. Okay, so that's the only difference that's between these two. All right, so let's see if we can clear up some of those problems about omega. So the omega isn't our actual frequency or our period. We relate those two to help us find one or the other. Either you know the frequency and period and you have to find omega, or you have omega and you have to find the period or the frequency. So let's talk about the problem we did yesterday. All right, so we have a weight moving at the end of the spring. The maximum displacement is 10 centimeters. Okay, and it takes 4 seconds for the weight to cycle. All right. So from this, we have a maximum displacement of 10 centimeters, and we have a period of 4 seconds. Okay. Remember too, I gave you a relationship between period and the frequency. It is a little strange, but in physics, in math, we use a capital T for the period. That I'm not sure why. Don't ask me why they don't use P. I don't know. Okay, so if you have the period or frequency and you want to find the other, you're just going to take the reciprocal. All right, there's a direct relation there. All right, so from yesterday we had a period of 4 seconds, which means we have a frequency of 1/4, 1 out of 4 cycles per second. I can't spell. Okay, so again, it takes 4 seconds for me to do 1 full up and down, which means in 1 second, I get through 1/4 of the cycle. Okay, that's what frequency means. All right, so now I want to write an equation that models the situation. So the first thing you're going to ask is, did we start in neutral position or did I start up or down? Right, and from what we did yesterday, okay, we started in the neutral position. So that means we're going to start with sine. Okay, so we're going to start with the sine position. So my equation, my formula that I'm going to set up is the displacement equals a sine omega t, right? That's just the rule. That's how it's set up. Now the a is simple. The a is just our maximum displacement. Right? In our case, it is equal to 10. Now, depending on how we start, tells us if it's going to be positive or negative. If we start our direction going down, it'll be a negative 10. If we start our spring going up, it'll be positive 10, right? So for that, we'd have to look at the diagram. So because it's being pulled down, I'm going to make it a negative 10, right? Because those first few, tenths of a second, I'm moving in a negative direction. So I'm going to make that a negative 10. Right? It's just like the amplitude. If I wanted to know the amplitude, it would just be the positive 10 because we take the absolute value like we saw when we were dealing with that. Right? So it's going to give me d equals negative 10 sine. So now we have to find our omega. To find the omega, we're going to use one of these two. So you're going to either set the period equal to 2 pi over omega or the frequency to omega over 2 pi. It doesn't matter which one we do. I'm going to do period since we were told what the period was, right? The period was 4 seconds. So again, the omega isn't 4. Okay, it's going to be 4 equals 2 pi over omega, and now we have to solve for omega. We have to solve for that variable. So I multiply both sides by omega. I get 4 omega equals 2 pi. I divide by 4. And I get my omega is pi over 2. So plugging that in, I get my displacement equation to be -10 sine, and I'll say, yeah, pi over 2t. Now this equation will tell me where the weight or the end of my spring is at any time. Right, so if I wanted to find out where is the spring after 10 minutes, right, I'd plug in 600 here for 600 seconds, which is 10 minutes, and I could find out exactly where that is. Right, it's only going to be between -10 and +10 because it's just bouncing in between those, but I can find exactly where it is at any given time. Right. So if I wanted to know 21 seconds, I would plug it in. Right. I would make sure I'd have to be in radians. Okay. We are not talking about degrees right now. We're in radian mode. So make sure we are in radians, and I could just type this in as I see it. -10 sine. We'll do another parentheses, pi over 2 times 21. So actually at 21 seconds, I'm back at -10. Let's change this up real quick. 21 pi over 2. Yep. Okay. So we may be asked something reverse. They may give you an equation, and they may ask you to elaborate on that, right? So here we're going to consider the equation for a simple harmonic motion. D equals 6 cosine, that's a 3 pi over 4 t. So let me make that a little clearer. All right, so now that we have the equation, all right, and now that we know what everything does, we can find a number of things. Right, so they want us to find the maximum displacement. Well, that's just like finding the amplitude. Right, it's just the number that's in front. Now, they didn't tell us any units, so I'm just going to say the max displacement is 6. If they tell you, you're dealing with centimeters or feet or whatever, then it would be centimeters or feet. Then they want us to find the frequency. So if they're asking for the frequency, that's a little easier. Okay, then we use the equation omega over 2 pi. Right? So from our equation, we know omega is the number that's in front of the t. That's going to be 3 pi over 4. So I have the frequency is 3 pi over 4 over 2 pi. The pi's cancel out. So I have 3/4 times 1/2 if I do a keep change flip. So 3 over 8. So let's think about that for a second. 3 over 8 cycles per second. So in 1 second, whatever I'm looking at goes through 3/8 of a cycle. So we almost make it halfway through a full up and down, but not quite. They didn't ask us, but we can tell from this that the period is 8 over 3 seconds. So it takes a little more than almost 3 seconds to make one full rotation. All right, they didn't ask us for this part though, so that was on the side. Now they want us to find the displacement at t equals 4. So now you just plug in 4 here. Okay, like I said before, I can find it at any time. This is actually nice. The 4's cancel out. So we're finding 6 cosine of 3 pi. And we're at -6. So that means we're at the bottom of our rotation, or of our whatever it's happening. Right, and then the last one, what is the least value of t for which d equals 0? So this is something that we haven't done yet. So let's take a look at that. So I want to know, when is the soonest time, or when is the quickest time, the shortest time that we return to that origin spot? All right, so we're going to set the equation equal to 0. Now we're going to solve. So I have the 6 out front first, so I'm going to divide both sides by 6. 0 divided by 6 is 0. So now I want to get rid of the cosine, so our inverse trig comes into play here. Now this is going to give us a lot of answers. There's a lot of instances where the cosine of some angle gets us 0. Right? So we're looking for all the x-intercepts of cosine equals 0. And I'm running out of time. All right, so I'm looking for the soonest one. So the soonest one would be pi over 2. That's the earliest one. Why wouldn't I pick this? Well, if I'm talking about time, I'm not going to have negative pi over 2 time. Okay, it wouldn't make sense, right? So I'm only looking at the positive values. So the first value is pi over 2. I would have 3 pi over 2 and 5 pi over 2. But I'm looking for the quickest one, the earliest one. So I get pi over 2 equals 3 pi over 4t. And then we would divide both sides. and we would get 2/3. So in 2/3 of a second, in 0.666 seconds, whatever we have, the weight, the ball, whatever is moving in harmonic motion, goes from the top to the origin, to the center. All right, that was a little bit of stuff. Any questions? I know we're out of time. Oh, and I never put a DOL. Awesome. All right. So I am going to give you something for homework tonight. Probably. Yeah, I'll figure it out. It'll be a problem like this. I don't know if I'm going to ask you to set up an equation or if I'm going to ask you to evaluate one like we just did. I got to think about that for a second. But do check the Google Classroom later tonight, later this afternoon for that. And we'll meet tomorrow to go over that problem. All right, guys. Have a good day. I'll see you tomorrow.